Hi, I'm Michela Meister, and I'm here today with Sloan Nietert to discuss our work on learning with comparison feedback, online estimation of sample statistics. In this work, we explore an online version of the noisy binary search problem studied by Karp and Kleinberg. We imagine an algorithm is faced with a stream of data, but can only interact with each data point through a single threshold query. This binary feedback is reasonable in settings where the data provider may be unwilling to provide their exact value. For example, consider survey participants providing information about sensitive topics such as salary or health. More formally, let's suppose we have a universe of elements 1 through n, and at each time step t, an adversary selects a sample x sub t. Then the algorithm selects a query q sub t with no knowledge of x, and then the algorithm receives feedback indicating whether x is at most q. Then the algorithm outputs a median estimate of the sequence of samples so far, and the adversary observes the query that the algorithm chose. In this setting, we assume that the adversary is adaptive and has full knowledge of the algorithm, but not of its random bits. In particular, this means that the sample x sub t may be a function of the history so far up through time t minus 1. And in the setting where the sample x sub t is drawn from a fixed distribution d, this reduces to the noisy binary search problem studied by Karp and Kleinberg in 2007. And there's an algorithm for this problem with expected runtime log n over epsilon squared for an accuracy parameter epsilon. So how will we evaluate these median estimates? We're going to evaluate the median estimate at time t with respect to f sub t, the CDF of the discrete distribution x sub 1 through x sub t, all of the samples so far in the sequence. And this error is approximately the difference between 1/2 and the CDF value at the median estimate. The chart on the right describes this error metric best. So you can see that any element whose CDF value is within epsilon of 1/2 has error at most epsilon. Those elements are considered epsilon good medians. We say that the query complexity of an algorithm is the minimum time t naught, such that for all t greater than t naught, the error of the median estimate at time t is at most epsilon with probability at least 3/4. Our main question then is, what is the query complexity of online median estimation in the online comparison feedback model? And next, I'll describe the algorithm for our upper bound, which achieves query complexity n log n over epsilon squared. And then Sloan will go over our lower bound, which shows that no algorithm admits query complexity less than n over epsilon squared. And again, in the stochastic setting, where the adversary is constrained to choose its samples from a fixed distribution, there's an algorithm with expected runtime log n over epsilon squared, because this reduces to the noisy binary search problem. So the high-level idea for our algorithm is to draw queries uniformly at random, and with these queries, construct an estimate of the CDF of the discrete distribution x sub 1 through x sub t. So specifically, we're specifying that at each round t, the algorithm will draw its query q sub t from the uniform distribution on the n elements. So I'll now describe how we compute the estimate of the CDF at round t. So given queries chosen uniformly at random and given binary feedback for each of these corresponding rounds through time t, for each element I, we're going to compute estimate of the CDF at element I, which sums over all of the time steps where we queried element I and where the sample was at most I, and then averages this sum by or divides this by the expected number of queries per element, which, since there have been t rounds and there are n elements, is t over n. And it's fairly straightforward to show that this is an unbiased estimate of the true CDF. And given that this is an unbiased estimate, for large enough t, we can show that our estimated CDF is close to the true CDF with high probability. And then what we're going to do is we're going to output the median estimate at time t according to the median of the estimated CDF. And since our estimated CDF is close to the true CDF, the error of this median estimate is at most epsilon with probability at least 3/4. And so this establishes our upper bound. And now Sloan will go on to describe our lower bound.
So Michela just presented an upper bound giving query complexity n log n against even adaptive adversaries. In the stochastic setting, though, only a logarithmic number of samples were required for median estimation. So the natural question, can we avoid this exponential increase? We provide a negative answer, actually, with a lower bound that uses just an oblivious adversary, so long as epsilon is sufficiently small with respect to n. Formally, our theorem states the following. In the online comparison feedback model, no median estimation algorithm admits query complexity little o of n over epsilon squared, even against oblivious adversaries. And the adversary that we construct to prove this result exploits a regime of small epsilon. So our proof takes the following structure. First, we reduce the seemingly harder problem of full CDF estimation to median estimation. Then we reduce Bernoulli testing, a particular Bernoulli testing problem, to CDF estimation within our model. And from there, basic KL lower bounds imply our desired hardness result. To produce our lower bound, we need to construct some adversary which is sufficiently challenging for median estimation algorithms. In particular, we consider an oblivious two-phase adversary B, parameterized by a distribution D and a quantile tau. B is constructed so that if an algorithm A maintains good median estimates when faced with B, then it must be internally maintaining good estimates for this quantile tau of D. So in the first phase, for rounds 1 through t over 2, our adversary simply returns samples from this distribution. This phase is where the algorithm has to learn about the distribution. In the second phase, the adversary returns the largest possible sample n for a fraction tau of the phase length, and then the adversary returns the smallest possible sample 1 for the remaining rounds. To make this choice a little more intuitive, let's examine the CDF of the samples produced by the adversary over the course of both phases. Suppose that the distribution D has CDF G, then the CDF induced by samples in phase 1 is approximately equal to G, as long as T is sufficiently large. Here's a graph of a potential CDF along with its median. Now, if tau equals 1/4 and the remaining samples are split between 1/4 at n and 3/4 at 1, the final CDF at time t is roughly a shifted and scaled copy of G, as illustrated on the right. Note that the median of this final CDF is approximately the 1/4 quantile of the distribution D, which exactly aligns with our initial goal. Good median estimation against the adversary corresponds to good quantile estimation for the distribution. And we prove this formally for any choice of quantile tau. Now imagine that our algorithm is faced with such an adversary, but the quantile tau is actually selected uniformly at random between 0 and 1. Now success here requires accurate estimates for many quantiles. Furthermore, these distributions that we consider in the next part of the reduction are near uniform, so good quantile estimation roughly corresponds to good CDF estimation. We make this connection quite explicit in our proofs. So the second step of the lower bound is now a reduction from Bernoulli testing to CDF estimation against just a stochastic adversary. So the basic idea is the following. If xt is sampled from a distribution with CDF f, then the binary feedback we get when we query q is actually a Bernoulli random variable with mean f of q. Hence, learning the value of the CDF at Q corresponds to estimating a Bernoulli mean from samples. And this is something that we understand really well. So by selecting the distribution D from an exponentially sized family, this requires epsilon to be bounded by 1 over n. We show that maintaining good CDF estimates is roughly equivalent to good sample complexity for a simple Bernoulli testing problem. And from here, we can use standard KL lower bounds to say that at least n over epsilon squared coin flips are required for the Bernoulli problem, which corresponds to the desired query complexity lower bounds for CDF and hence median estimation. So in addition to the results presented so far, we also provide more specific lower bounds that apply for all regimes of epsilon. Furthermore, we examine the constant epsilon regime in a bit more detail and provide some interesting open questions. And we also explore the case of mean estimation. So, in summary, we've presented this natural extension of noisy binary search as an online learning problem. We've presented simple algorithms providing accurate estimates with nearly matching lower bounds. Looking forward, we have some generalizations for graphs and other high-dimensional settings, and we hope that exploring intermediate regimes of restricted adversaries might lead to more interesting and sophisticated algorithms. So that's all I have for you today. Thanks so much for listening, and we look forward to any questions.